Hello, class. Just making sure that my microphone is working, and we are going to have a lecture on a very important topic. Now, I want to point this out because this is an important topic. I want to even point that out beforehand, and I want to point out also how important centroids were. And the reason that oh, wait a second, let's turn on my timer. Boy, I'm almost on top of things. Excuse me. So what I want to do is first talk about why we're doing this, because later on we're going to be looking at members like this. Let me just, this is just an I-beam that I'm drawing. Oops, not a very good I-beam, I must say. But we're going to have an I-beam, and when we do the I-beam, we're going to have figure out what a neutral axis is, and the neutral axis, I'm going to draw this here for an I-beam, because eventually this is where we're getting to at the end of the course, right? Is we're going to be looking at Flecture diagrams for I-beams. So we'll be looking at several different things. I just want to point out two things. A cross section like that of the I-beam, I'm going to talk about that in just a second, and also we'll have this beam that is supported, right? In fact, there's three different ways to support it. We'll talk about all those, but I'll talk about the most simple way of supporting the beam, right? And that's with a roller at one end and a fixed position at the other end, right? I'll just draw that so it's all, that's connected, and that's sort of, floating on something over here. So this would have various different forces pushing down on this, as we're loading this beam. And this would be the beam, right? I'm just going to sort of draw this in 3 dimensions. This would be the beam, right? And let's just say that it's going down. It's a long beam. And that's going to be the beam that then extends, and that is the beam. If I was looking at the beam from that end, this is what the beam would look like. That would be the axis that would be coming out of the end of that beam, this axis right here. So we're looking at the cross section of the beam, right? Now, what we know is that I should say, let's just say that, let me draw this. This is, y equals 0 down here at the bottom. So what we know is that y bar of the neutral axis, we'll find this out, I'll actually derive this, is equal to y bar of the cross section, right? So that tells us where the neutral axis is. Now you can see in this drawing that I have of the beam and the loading on the beam and everything else, that it's symmetrical about this. So we could see that the neutral axis or the centroidal axis of this combination, with this flange being the same thickness as this flange, is the same thickness of this flange. It's all symmetric about this centroidal axis. But what if I had a beam that looked like this? Oops. Right? What if I had a beam that's not even symmetrical about the, okay, whatever, it looks like that. It's supposed to be symmetrical, but anyway. So you can see now that because this is larger down here, for a beam like that, and you're saying, well, who would make a beam like that? How about the railroad? Isn't that a railroad? Isn't that the bottom that's nice and thick, and then up on top we've got, our rail that the subway rides on? Isn't that a rail? So all of a sudden, instead of this distance here, let's call this distance y1, right? And this distance here, y2. I think everybody can see that now, because this is thicker down on the bottom, the centroidal axis, which is also the neutral axis, I'm telling you the punchline before we get to those lectures, is going to be down there. So that is why centroids are important. So determining centroids of plane areas, right? I'm gonna put a box around that. We'll put a couple stars in there, because later on, I want to show you the application that you're going to be using that in, and that's going to be what we're going to find as we go through strength of materials and look at the Flecture. This is going to be under the Flecture topic later on. Now, moments of inertia for plane areas. We're going to be looking at moments of inertia for this too. And why? Because the Flecture formula that tells us the stress, right? The stress, and it's usually sigma that we write it on, is going to be the bending moment times y divided by I. Now, what is I? I sub x and I sub y are the moments of inertia for plane area. So we're going to look at, I happen to have different colored pens now. Yeah, let me find one that looks good. There you go. So we're going to be looking at this cross-sectional area here, and we're going to, I mean, you know, I've drawn it as a three-dimensional bar, but what we're going to be looking at is just that two-dimensional area, right? And that's why we're trying to find out how to determine centroids of plane areas. We're trying to figure out moments of inertia for plane areas, because the moments of inertia for that cross section are what we're going to use, and we're going to find that out for this. And you can see that this really is just three different areas of rectangles. I think everybody can see that. Did I lose my red pen? I didn't. There it is. See, so this would be one rectangle up here. This would be another rectangle here. And this would be the third rectangle down here. So we would have to find the individual centroids and moments of inertia of these three areas. And then we would have to translate them to the neutral axis. So portents of things to come. In other words, this is why you're learning this, because we're going to need this down the road. So having said that, and put you know, the idea that understanding how to figure out centroids, understanding how to figure out moments of inertia for plane cross-sectional areas is going to be important once we start to get into solid mechanics, which is the third part of this course. All right. Statics, though, prepares you for that. So I don't have to really cover this in the future. However, I'm going to go through the derivations of this, and then we're also going to look at it. Now, here's one thing that we know, is that if we were to look at any cross-section, let's just take a cross-section of a rectangle, right? All right. Now, I'm going to take that rectangle. I'm going to say, well, this is just a very thin piece of metal, very thin, like a sheet metal, right? Sheet metal, but a very strong sheet metal. So I've got a sheet metal here. Now, if I was to take this sheet metal piece and I was to weld right across the centroid, right? This is the centroidal axis, so this would be Y bar. If I was to weld across there just a piece of wire, right, a thick piece of wire, and I was to rotate that steel around there, sort of like a little flywheel, right around the center. And then I was to take another one and I was to actually weld a piece of metal down here. And I took that other one and I rotated it around there, which would take more torque to start that rotating and to keep it rotating. And this is an intuitive question, right? I'll just call this y of the base. I think everybody can see that if I really welded it along the center and I started spinning, and it'd be much easier than if I was to weld it along the base and then start spinning around. Plus, it would cause a vibration if I were to do that, wouldn't it? But it would be harder because the mass, the center of gravity of this would be further out here, right? Whereas the center of gravities of these two masses are relatively close in to that axis I'm spinning it around. That's true about moments of inertia for plane areas. And that's what we always see. So the moment of inertia, I'm just going to call it the moment of inertia, right, about y is always going to be less than the moment of inertia about anywhere else, actually, but in this case, y sub b, right? Always going to be less. In fact, it's going to be the minimum. Right? I should put y minimum. Okay, you know what I mean. So it's going to be the minimum whenever it's at the centroid. So if we can find the centroid of a cross section, it's always going to be smallest there. And that's what I want to do first. I want to look at a rectangle. Okay. So what I'm going to do is I'm going to look at, and of course I had to draw it 5 high, didn't I? So I had to go right through the middle of my grid there. But yes, what I want to do is I want to look at it right at the centroid, right? And you can see the centroid to be right there, and then the x centroid would be right there, right? Does everybody see that? And also, this is going to be my x and my y axes for that. And so if this is 0, 0, right in the middle here, then we're really going from minus, let's just call this minus b over 2, and that would be plus b over 2, and then this would be h over 2, and this would be minus h over 2. Does everybody see that? Because this is 0, 0 right in the center here. So, and I'm using that because I know that the centroid is right in the middle. So I'm using that as the center of my Cartesian coordinate system too. Let's look at the definition of moment of inertia, right? So I sub x, the moment of inertia around the x-axis, is going to be the integral of y squared dA. And the moment of inertia about the y-axis is going to be the integral of x squared dA. We've seen similar integrals like this when we were working with the centroids, right? And so here we see it again. So what I want to do is, the first thing I want to do is just derive using this. Let's just look at I of x for the rectangle that I have here. Okay, I'll put rectangle. I'm not going to write that all the time though. And that means that I have the integral, right, from minus b over 2 to plus b over 2 of y squared times dA. Now, what is dA? Let's just look at dA for a second before I just write dA and then have to write the whole thing all over again, right? What is dA for this? Because it's really, you know, we're looking at a small sliver, right, of this, right? Does everyone see that with dA? And so my dA is going to be dy times b, right? Isn't this distance here? Because it's b over minus b over 2 to plus b over 2, so that would be b, wouldn't it? Okay, so b dy. Now, of course, that's dA for this. We have to look at dx the other way, but I'm sure that you can do that yourself anyway. So let's write that in. So that's going to be b times dy. We can take that b outside of the integral, can't we? So that means that we've got b, and I'm just going to put a bracket here because everything else is really done inside here. And this is going to be y cubed over 3, isn't it? So that's going to be b, wait a second, y cubed over 3. And so that's going to be b over 2 cubed over 3 minus a minus b over 2. I should have just put that there. Cubed over 3. Right? And so I've really done 2 steps there at once. I've got the b over 2 cubed divided by 3. And then I've got the minus b cubed over 2 divided by 3 too. Right? Does everybody see that? Okay. What if I, b, just a second, let me, oh no, that's supposed to be h over 2. Oh, I switched the things around. Yep, so mine, I switched my h's and my b's around from the workbook that I'm taking this out of, but that's okay. It should just take me a second. Yeah, I'm sure. And now, of course, my my thing doesn't work correctly. Oh well. H and minus h over 2. It still looks like a b. And then that's going to give me, and this should be, why would that, just, let me look at this for a second again. Yep, I'm going from minus h to plus h. That's true. And that should be, I think that is a b. So I was right there. I'm transposing all of these things, and that gives me, that should be a b. Just looking at the other things, and then these should be h's. So h and h minus h. All right. Before I go on, I just want to make sure that this all looks right, and who knows if, and of course my handy dandy thing is going off here. So this is going to be minus b over 2. So I'm trying to get my, trying to get all of these right, and I wonder if I even started. Yes, I did. Boy, at least I've got that going for me. All right, so we're finding about x, and so we've got y squared times b dy, and that I did have that right. So the b dy is correct, and the b here is correct. So I was still using the correct notation up here. And now what I'm doing is I'm taking this dA that I've got right here, b dy, y squared, and I'm going from minus h over 2 to plus h over 2. And this is those, why did that come back up as a b? H. Okay, I'm sorry about that. But originally I had an A and B in here, and so the B, switched. So I missed changing it on one of the integral signs that I had here, and that's what screwed me all up. All right. Now I could take the 3 out of there as well, and I think I'm going to actually do that step, because instead of jumping over a step, sort of like I did, I don't want to do that again. Let's just say that. So I've got B divided by 3, and then I've got h cubed over 8 minus, and this is a minus now, and this is going to be minus h cubed, so that would be minus h cubed, because I've got minus h times minus h times minus h. I'll write it here, minus h times minus h times minus h. There's 3 minuses there, so I end up getting a minus h cubed. So minus h cubed over 8. All right. So so let's simplify this. So I have h cubed over 8, so I've got bh cubed over 24 minus a minus, so that's a plus, bh cubed over 24. Well, that would give me 2bh cubed over 24, so let's just call it bh cubed over 12, right? So bh cubed over 12, and you can see that the units here are going to be in meters to the 4th. I'm sure that you always wondered what meters to the 4th units would look like. That's right. It's the moment of inertia for plane areas is meters to the 4th, right? You're always wondering, what's meters to the 4th? Well, this is it. And it tells us a lot, and it helps us out a lot. So that's the moment of inertia for a plane area. There's moments of inertia for mass too, mass moments of inertia, and we'll talk about those later as we talk about dynamics. But right now, we're just picking this up. So that would be I sub x. Now what I want to do is I'm going to do another I sub x, but this time, right before with the dots, that was this. So the top part of this is really all about having the Cartesian coordinate system right in the center, right, of right in the center. But now what I want to do for this one is move the Cartesian coordinate system over here. And so now I want x to be down here at the base and y to be going up that way. And so it's going to change this, isn't it? Because this now is going to go from 0 to h. And this is going to go from 0 to b, right? Does everybody see that? So from 0 to h with the new coordinate system, and from 0 to b, or 0, I suppose, you know what I mean, 0 to b, not 0 to 0. Yeah, forget that one. Over there. So now our integral, the extents of our integral are just going to be different. They're still going to be the same distance, but they're they're going to be written differently. All right, and what I want to show you is that along this base here, right? We found that along really, I'm going to put along the centroidal axis, right? I'll put it up there. But this was along the centroidal axis. Now what I'm going to do is I'm going to find the x, but it's going to be along the base for the rectangle, okay? We're going to derive it from the base. So just like we're doing down here, and what would we expect? We would expect it to be greater than this, right? Isn't that what we're saying? Is that when we're looking at well, yeah, when that would be x. There we go. So so when we're looking at the moment of inertia about the x-axis, right? We would expect it, these are right, don't worry. We would expect it to be much greater around the base than it would be around here. And that's what we're going to see. That's what we're going to see by deriving it with this. So now, what is dA? I'm going to put dA over here. We're going to use it in just a second, but you know, really it doesn't change, does it? dA is still going to be dy, and it's still going to be by. So b times dy. So dA stays the same. And now I've got I of x about the base is now going to different extents. It's going from 0 to h. So instead of going from minus h over 2 to plus h over 2, I'm going from 0 all the way up to h. I've got y squared still, and I've got b times dy, right? And of course, we know that b times dy equals dA, right? All right. Well, let's solve that. We can pull b outside, and then I'm going to actually write this out, 0 to h, because I don't want to, yeah, 0 to h, and then I've got y squared dy, so I've got b times y cubed over 3, evaluated from 0 to h, right? And so I about x about the base is going to be h cubed over 3, so b h cubed over 3. See how easy that was? And so that's the moment of inertia about the base of this. So for the base of a rectangle, the moment of inertia is bh cubed over 3. And for it at the centroidal axis, it's bh cubed over 12, 1/4 of what it is at the base. Does everybody see that? 1/4. Now, I want to show you something. This is the transfer formula. Oh boy. Transfer formula. I'm going to put it up here because I wasn't sure I was going to get to a point that I was going to use this today, but I think this is a good place to introduce the transfer formula so that you can see it for the rectangle. I'm going to still try to, let's see how much, well, maybe not. I won't derive it in this lecture probably for a triangle, but I'm going to derive the moment of inertia for the triangle as well. And I'll do that maybe in the next lecture. But what I want to do now is I want to introduce the transfer formula. Here's what it is. It says that the moment of inertia about any other axis other than the centroidal axis, right, is going to be equal to the moment of inertia about the centroidal axis. A lot of times you'll see even a line over that, or you'll see lines over, these sometimes, plus the total cross-sectional area times the distance between these two axes squared. All right, now let's apply it. Let's apply this. Let's say that the moment of inertia about the base, right, is going to be the moment of inertia about the centroidal axis plus the area of the rectangle times the distance squared between the two axes. I think we all know what the distance is between the two axes, right? D is going to equal h over 2, right? And d squared is h squared over 4, of course. So let's go back up here. So we've got bh cubed over 12 plus the cross-sectional area of a rectangle, which is BH, right, times the distance, which is h over 2. So I'm just going to say h squared over 4 because that's 2, right? H squared over 2 squared is, anyway, so we get that. And so if I look then at the at simplification of this, I've got BH cubed over 12 plus, well, I'm going to put it here, BH cubed over 4. But really, if I make it over 12, isn't it 3, right? Wouldn't 3 BH cubed over 12 be the same as BH cubed over 4? Right, so it's common denominators, that's the reason I'm doing it. And so that would give us 4 BH cubed over 12, or BH cubed over 3. Right? I'll use the red pen. There we go. So we got it this way by, just looking at that. And then we can also use the transfer formula to do this too. And that's the great thing about it, because, we're going to have to transfer our moments of inertia, right? Didn't I say that each of these will have a moment of inertia, each of these rectangles? And so we're going to have to transfer that moment of inertia from here down to the neutral axis. We're going to have to transfer this one from here up to the neutral axis. And what if, like this, we have we have all 3 of these, right? This one right here, maybe its centroid is there. This centroid is up here. This centroid is down here. So all of these will have to be transferred. Even though it's just a little bit, it still has to be transferred to the neutral axis when we're doing our summation of moments of inertia for the cross-section of an I-beam. You see why we're doing this now? Because that's where this is going, is eventually to understand structural engineering concepts and stresses and strain in materials and everything else, right? Okay. The next lecture, I'm going to look at deriving the moment of inertia for a triangle about its base And then we're going to use the transfer formula to transfer that to its centroidal axis and finding out what the minimum moment of inertia is going to be for a triangle. Okay, that's going to be the next thing that we're going to do. And then we're also going to look at not only moments of inertia about the x and the y axis, but we're going to look at moments of inertia about the z axis, right? We look at the moment of inertia coming out from the end here. And so the different moments of inertia, you know, that we're going to have is we're going to have a moment of inertia about the x-axis, a moment of inertia about the y-axis, and a moment of inertia about the z-axis. The moment of inertia about the z-axis is called J. And so that's J is the polar moment of inertia. And it equals I sub x plus I sub y, right? And what do we use that for? When we start to look at shear stress in a torsion rod, right? We have shear stress in the torsion rod equals T, the torsion, times the radius of the torsion rod divided by the polar moment of inertia of the torsion rod, right? So that's why we're going to have to understand the polar moment of inertia as well as the two moments of inertia about the x and the y axes. All right? Okay, see you in the next lecture.